So thanks for coming to my presentation, even though it's remote with some technical problems. Okay, so I'm going to present Actema, which is a graphical user interface for building proofs interactively. This is a prototype we've been building for a few years with Benjamin Werner, who was my PhD advisor. And yeah, so let me show you the system with the demo. So let's close this. So this is some IDE for the Rocq proof assistant. Because we have integrated the interface with Rocq, as I will explain. So let me show you how it works. First, I need to import this plugin called Actema. It is a Rocq plugin. And yeah, basically that's all I need to set up. And now I'm going to show you this basic example of program verification. So I'm going to prove the correctness of the insertion sort algorithm expressed as like a pure function on list of natural numbers. So I start with a bunch of definitions. So I define these predicates. So there are these low predicates defined recursively on lists. So basically, it just says that this natural number n is lower or equal to the head of the list, if there is one. Then there is sorted predicates, which uses low predicates to define a list as sorted if the first element is lower than the second, like the head of the sublist, and recursively like this, the first, the second, and the third, etc. Then we have this construct of this is here just requirements of the like a limitation of the current implementation. So we just wrap the if then else of Rocq into this if then else constant. Because it's otherwise Actema won't be able to display it. And the heart of the definition will be the insert operation, which is defined again recursively in lists, and we just like put n in the list so that it's after every smaller element and before every greater element. Okay, so now onto the proof. So here we want to prove this basic invariant that if we insert something in the list, it will preserve sortedness. This is this part of the statement. And then, as is well known in program verification, the hard part is finding the right invariant with enough information so that the proof can go through. So this is this part, which is a bit tricky to find, but yeah, here we just assume it. Okay, so now I will call this Actema force tactic, which will allow me to send the current proof state to the Actema interface. Okay, so I just need to redo it. Yeah. So here, it's not completed yet. It's not highlighted in green because it's waiting for me to do the proof graphically. Here it is. So this is the Actema interface. So this is, you can think of it as a view for, like an interactive view for the proof state. So here I have my conclusion as a red item and move it around. And what I want to do is a proof by induction. So I'm going to select this sub-expression, which is this universal quantification over the list L. And then I can open this contextual menu, which proposes me to apply this induction tactic. So I proceed, and I end up with two sub-goals, which are represented by these two different tabs. So from here, you can see that a bunch of context is added. So this is a recursive case. So I have a bunch of variables. N is the element I want to insert, A, the head of the list, L is the tail, and then I have this induction hypothesis as a blue item. So let me focus first on the base case. So here I want to simplify my conclusion, like to unfold all the definitions. So I can select the whole statement. And then you see when I open the contextual menu, I only have this simplify action, because Actema is smart and is able to see that I have selected this sub-expression, and it will only propose relevant actions that are applicable to this sub-expression. If I can simplify it, then actually this is a trivial statement. So I can just introduce this quantifier by double-clicking. I get this new m variable. Then I can click on the implication, introduce this assumption, finally click on the assumption to apply, because it matches exactly the conclusion, so it just solves the code. Then I can simplify again my conclusion. Actually, it's not really simplified. It's still pretty hard to read statements. But nevertheless, I can just click on it and see what happens. Here, I get this new assumption, which I can split into two assumptions by clicking again. And then actually I can combine already these two assumptions, sorted L and my induction hypothesis. So I can grab it and combine it through drag and drop like this. So you see the premise matches the other assumption. So when I release the mouse, I do this forward reasoning, giving me a new assumption where the premise has disappeared. But I can remove this one. I won't need it anymore. And now, so the conclusion is still quite complicated, and this is because I'm not able to simplify to compute this if then else expression, because I need to reason by case on this, which states that n is smaller or equal than a. This is just Boolean comparison. So let me reason by case. I get two new sub-goals, case where it's true and the case where it's false. I'm just going to do the true case because I'm running out of time. So yeah, now I can simplify the whole thing. And I get this a bit simpler expression. So actually, I can start dragging the conclusion. And maybe you can see, I hope it's visible, that in the context, some sub-expressions have been highlighted, like squared, which indicates that I can use these assumptions to simplify the conclusion. I can bring it, for instance, to this assumption. I see that it matches some part of my conclusion. So yeah, this is a kind of backward reasoning. So this has simplified away the low proof obligation. Then I can also simplify sortedness. And then, so I will need to prove this, that n is smaller than a. Actually, it's just this assumption, right? It's just expressed with a variant, this is propositional comparison, which is different in Rocq than Boolean comparison. So I need some lemma which relates the two definitions. So here I have this selection, and I just need to add some keywords that I will use for searching the lemma. So I'm gonna like LEP for Boolean comparison. And when I hit search, okay, so if I remember correctly, there is a bug in the current prototype. So first, before doing this, I will just click on this done button. So this allows me to illustrate another part of the interface. So if I click on done, yeah, so I can go back to my proof script. So now I'm gonna replace Actema force with another tactic called Actema. So basically, when I execute this tactic, it will just replay the whole sequence of actions I've done in the interface, which has been recorded somewhere on disk. I can look here at this Actema the proofs folder where I have a bunch of nonsense. It's just like an encoding of this sequence of actions in different files. Okay, so it looks up the relevant file by just looking at the shape of the proof states. and replace sequence of actions. Okay. So I can focus on the first goal, for instance, and then I can go back to my graphical interface. All right, so this is the first goal where n is smaller than a. So again, let me do the search. I don't know why it's saying two subterms selected. I guess a little bug again. This is still prototype, right? Yeah, so now it works. I have these, immediately I can find, so Actema was able to filter based on the selection and find the relevant lemma. So I can apply it through drag and drop again. And now, so this is just, I mean, this matches exactly my assumption, but I want to illustrate here that I can use the assumption by clicking on it. So if I click on the left-hand side, it will rewrite in the conclusion into the right-hand side. Okay, so now I get this trivial statement. I can split. I focus on this sub-goal. Then I click again to apply reflexivity. And yeah, this is a trivial statement. Okay. And I'm done. Okay, this was a bit long, but I've proved this first case of my invariant. I'm not going to do the second case. I'm just going to apply this pre-recorded sequence of actions. Okay, I don't know why it can't find it. So let's just admit it, right? But I mean, I could do it. Yeah. What's happening? Yeah. Sometimes it's a bit buggy, the interaction. Okay. So let me just write admit. So just to show you that I indeed have correct proof, I can show you at this stage, I guess this comment should work. Yeah, so I do have some proof term, which is printed here. It's very ugly, but I do have some proof term that has been compiled from my graphical actions. Okay. So I guess I'm going to stop the demonstration here. I mean, I could go through with the last part, but yeah, I guess you've seen most of the features I wanted to showcase. So in a nutshell, this paradigm works by, but it's completely graphical. I mean, you can switch between proof scripts and the interface if it's needed, but in the interface, everything is done just with gestures. So proof is just a sequence of gestures manipulating the statements in the proof state. And the nice thing is that you get this kind of unified syntax where you just have to click on some statement to apply introduction or elimination, and it will look up the relevant rule without having to remember the exact tactic. And then for drag and drops, you have this forward distinction. So if you combine two hypotheses together, it will capture a form of forward reasoning. And if you bring the conclusion to some hypothesis, it will be backward reasoning. And you can also prove, so I proved this in my PhD thesis, that these actions, they form in themselves a kind of proof system, which is sound and complete for intuitionistic higher order logic, which is nice. So I guess I don't have a lot of time left. Yeah, so let me talk very quickly about how the system integrates the interface with the Rocq proof assistant. So this is the architecture of the system. So it's pretty generic. You see, like the Actema interface is pretty well separated from the Rocq proof assistant. So it could work with other proof assistants like Isabelle or Lean or whatever. As soon as you have this possibility to execute step-by-step tactics. And so, yeah, basically, the user will interact either with the IDE, like with the proof script, or the front end of Actema. So Actema is just a web app. The front end written JavaScript and some backend written in OCaml and compiled it in JavaScript with JS of OCaml. And important part is that we have a plugin also written in OCaml, a Rocq plugin, which will allow to interface Rocq with Actema. So it will retrieve some information from the proof state and send it to Actema, which will answer back with the list of the sequence of actions performed in the interface. And sometimes also the plugin will read some files on the file system if you want to re-execute recorded actions. So yeah, this is just a bit more detail. Okay, I'm not gonna go through this. The interesting part is how. So there are basically two different ways, two different scenarios. The non-interactive scenario is, as I explained, when the plugin will read some file based on the current proof states. Okay, so then it will get some sequence of actions which will be compiled into a tactic, and then the tactic will be executed, and then we get a new goal, and yeah, you have this loop. And you also have a similar loop when doing like this interactive mode where you do the proof in the interface. So you send, this time you will send the proof state to Actema. So actually, I didn't explain it, but Actema has this HTTP server so that it can receive requests from the plugin. So they communicate through HTTP. So you could imagine some scenario where the interface runs on a different machine than the proof assistant. Well, yeah, this is a bit far-fetched. But then Actema would render the goal. The user will start doing some gesture. And so the backend of Actema will try to think of interesting, relevant actions given the gesture. So it will render either some contextual menu of actions or maybe highlight some part of the context which can be used, some sub-expressions. And then the user will choose some action by ending the gesture. And finally, Actema will send this action to the plugin, and again, compile, generate new goal, and we start again. Yeah, I don't know how much time I have left.
So because of the late start, we're sort of at the end of the session now. If you want to go on for a couple of minutes, that's okay.
Okay.
Otherwise, we
So maybe I'm just gonna skip this. Yeah.
Yeah. Folks can engage with you further on Discord, and if you want to post your extended slides there as well, we can take a look at those.
Okay. Yeah, I can do that. So I'm gonna skip this part, which was a bit technical about how these drag and drop actions work. They can be quite complex. Yeah, basically the way it is compiled is by having this. So we have like click actions correspond to standard Rocq tactics like intro, destruct, etc. So this is quite easy. And drag and drop actions, you need some involved embedding of higher order logic, which is internal logic used by Actema. And then you can reason. So basically, you have a bunch of rewrite rules manipulating these formulas in order to implement the semantics of drag and drop actions. So this is a form of computational reflection, where you would just manipulate this embedding of formulas to compute either a new conclusion or a new hypothesis, depending if it's backward or forward reasoning. Okay, so let me conclude. What are the main use cases of Actema? So we think that this ability to have fast interactions with sub-expressions, which we can select very quickly instead of having to write some complicated like expression, like a pattern matching expression. You can just click on it here. It's much faster. So we think this enables rapid proof exploration. So when you don't know yet how to prove something, you can quickly iterate like this in the interface. Also, we hope that this is quite intuitive and discoverable. You can just click around and see what happens. So this could be useful in an educational setting. But we also hope that it will be of use to experts, because actually these drag and drop actions have a very powerful semantics. You can think of it as a kind of generalization of the apply and rewrite tactics, which works better in some cases. Like you can rewrite, for instance, under quantifiers, which is pretty difficult with most proof assistants. So a bunch of related works. So for instance, there is this proof widgets framework in Lean, which allows to define like arbitrary user-defined graphical notations that can interact with. There is also this idea of interactive proof states, but the architecture of the system is pretty different. It's very reliant on Lean's meta-programming abilities. And then you have also a bunch of people who have explored like more graphical or diagrammatic ways to interact with proofs, but usually it's only targeted at educational purposes. So you cannot do like complex proofs, and it's not integrated in an existing proof assistant. And then you have Scratch, which is nice also to learn like some programming language. So in the proof assistant, you could learn like the tactic language, like by combining blocks of tactics. But this is different from Actema because you manipulate the proof scripts and not the proof state. It's like a less static way of thinking about proofs. And here we have a more dynamic way. And a bunch of future work. So there's a lot to do. As you've seen, the prototype is a bit buggy, and there is some improvement to do on the UI. And also, it would be nice to have support for domain-specific notations in the same way that proof widgets does it, but it would make things a little more readable and manageable. And I guess, also it's difficult to edit a proof that you built graphically. This is called sometimes proof evolution, how to modify an existing proof. So we would need some kind of way to translate graphical proofs into tactics, which should be quite doable because this is what we do under the hood. Or even more interesting, maybe with some LLMs, we could like try to find some natural language translation, which is even more readable. And
okay, Pablo, we should.
We should wrap up. So I guess if you have any questions, you can ask them, and I will send the slides.
Yes, apologies for the late start and having to rush you there at the end, but there's...
No, it's okay, it's okay.
Yeah, thank you for the interesting talk. Well, I'll give you a round of applause here. Hopefully you can hear it.
Yeah, I can hear it.
And so I encourage